Well, I've just finished my next UHF beam experiment. So this was the idea after the 3D beam. The 3D beam had four main elements that were half a wave apart, widthwise and front to back, with additional reflectors further back. So to give a smaller footprint, my idea was to have just four elements and the front and back only being a quarter wave apart, and left and right being a half wave apart. And so, of course, that means the footprint is only a quarter wave long and a half wave wide, and no reflectors because the phasing is different. So the basic idea here is this one and this one are the back elements. So let's say here and here are the back. They fire first and they're half a wave apart, and they fire in phase. So as these are in phase, and because they're half a wave apart, by the time the wavefront from this one reaches this is now in the other phase, so there's a cancellation, and vice versa. So these are additive in the front back and cancelling to the side. But the thing is, by the time the wavefront gets to the ones in front of them, these ones are being fired exactly 45 degrees later. 90 degrees later. My bad. 90 degrees later. A quarter wave later. So by the time the wavefront travels this quarter wave distance and gets to here, these then fire. And these are also a half a wave apart, so they have the cancelling to the side. So the wavefront from here, these two, by the time it reaches these two, these fire and add to it. But consider the fact that when these two fire, unlike with the previous system, by the time the wavefront gets back here, this additional quarter wave trip, that's now 180, because we had quarter forward and then quarter back, which is a half. But the thing is, by this time, these are now in the other phase. So we have a cancellation. But forward and then to the next quarter here, and these adding, so it's additive forward, but the signal from this one is not additive backwards because of that quarter wave difference. So there's no need for reflectors if I've done this correctly. Now, of course, figuring out how to actually make this happen has had me struggling for a while, trying to come up with different techniques. And so I finally nailed it. So I've got the analyzer here. I'll put that on in a sec. So I've coming in with a half wave of 75 ohm coax. But then I've got, as you can see at a glance here, so we've got the two antennas at the back that fire first, and then these two that fire next. So the two ones at the back have shorter parallel feeds, you see, and the two ones at the front have longer parallel feeds. So it's roughly probably a bit over on all of them, but the difference between the back ones and the front ones are a quarter wave in length. So the back ones are a quarter wave shorter than the front ones, to make sure that the front ones fire a quarter wave later, according to this, and they're also physically a quarter wave apart. Now, there was a problem though. Of course, if I just run the coax straight to all of these four lines, let's say the active going to the top one of this one and this one, this one, this one, and the ground going to the bottom one of this one, this one, this one, this one, sort of thing. It did present a problem because I had, two different reflections 180 degrees out of phase because, well, quarter wave 180, half wave full. So 180 versus full, we've got 180 degrees out of phase. So so that posed a problem. And so how I've solved that problem is, of course, there's a timing issue, but RF has an amazing way of finding alternative paths, the least path of impedance. So some things can be optional, like this bit, okay? So, and this is how it's worked its magic. So basically, I've done what I've said before with the active going to one of all the balance lines and the shield going to the other of all balance lines. But also I've got another quarter wave section of a 300 ohm window line here. And what I've done is the active from the coax actually connects to both sides of the window line. But at the other side of that window line, a quarter wave later, each side of that end of that short quarter wave line connects to both sides of all of the feeders, right? So it would seem like a short, the active's going to both sides, but it is a quarter wave later. And the thing is, depends what's going on whether we're dealing with the reflection from this quarter wave, which is coming back early and out of phase, versus the reflection from this one halfway forward, halfway back, that's coming back in phase. And this little Duvalaki here is what solved my problem. So just stand by, I'll get the analyzer sorted. Okay, hopefully you can see here. So I've got a nice flat, fairly low SWR. This will be tunable. I've just got to, fiddle around a bit with spacings and stuff. But you can see here, I'm looking all the way from 470 megahertz all the way across to 480 megahertz. So a 10 megahertz span there. And the SWR is quite acceptable. At what did we have there? Sorry about this. 1.26 to 1 thereabouts. Okay, so I'll just sorry about this. Back out of there. Oops. And go back to stimulus. Start, and now I'll go from 430. Now it's not tuned, and the collinear elements are also not ideal for that part of the spectrum. But there we go, 430 to 500 megahertz. Of course, it won't behave properly too far out of its intended part of the spectrum. But what is that? Still quite, well, it's very broad on the SWR. But I'd imagine, its behavior on its pattern, because of course it's spaced and measured all for 63 centimeters, and also the collinear whips are built and all designed for 63 centimeters. Going too far off, it'll start to skew the pattern, might even change takeoff angles and stuff like that. Okay, wish me luck. I'll get it outside soon and do some proper pattern observations. 7.3, and thanks for watching.